that how I do it? Oh yeah, we're doing good things. Alright, welcome to the stream, guys. Oh, did I do the internet speed test? Internet's dying, but it's alright. Alright, so what's the plan today? The plan today is to combine... Yo, Kayoshi, welcome to the stream. Oh, rip, music too loud. Oh well. Talking while music playing is a bad idea anyway. So yeah, today the goal is to combine chemistry. I remember how slow it is to type. Oh, good times. Math and computer science. We got all three and we're going to try and bring them together. It's going to be epic gamer, hopefully. And wow, I'm getting input like rip. How did I live with this last time? I have no idea. Alright. So what we're going to do is we're going to look at something called free radical substitution from chemistry, and we're going to like mathemize it as much as possible, and then we're going to try and script it in Python, I think. I don't know which color to use for anything ever. So I guess I should probably start with talking about what free radical substitution, free radical substitution, yeah, that's it. So it occurs when you have, oh wow, it's thick. Let's go 4. When you have your halogen, which is diatomic, and it reacts with a alkane, which is just any compound of the form CnH2n plus 1, where n is a positive integer number. So this could be CH4, where it's just 4 hydrogens around a carbon, or it could be CH2, in which case it's, maybe I'll draw out methane, which is the first alkane. But yeah, as you can imagine, you just logically add carbons if you want to go across. So that's methane. If we wanted to add one more carbon, then it would be, be like this, and you can just imagine you got your H. What colour shall I use for H? So you got your hydrogens all around like this. You're not going to stay too long. You got anything you want to see in this topic? Do you know anything about this? Probably not, because it's extremely obscure to be honest. It's cool because programming. It's cool because programming. Like otherwise, it's like meh. But then when you realize that you can just shove it straight into Python, you're like, that's kind of cool. We're running out of space already. So anyway, you got your halogen, which is just a thing bonded to itself like so, and you got your methane. And they can react together to form. Why have I put +1? It's +2. Boop. To form CnH2n plus 1. So we lose a hydrogen, and that hydrogen gets replaced with our halogen. We get left over HX. So we can imagine this as like mashing out a hydrogen, placing it with a halogen. I don't know why I use X for halogen though. I kind of prefer bromine. Let's fix that, I guess. So that might have made sense. It might not have made sense. I don't know. Do let me know if nothing's making sense, because that's fair, to be honest. So we can replace X with bromine, because then we've got an actual thing to work with rather than just X, which looks kind of weird. Yeah. How do I explain radicals without going too much into radicals is the thing. I guess I have to a bit. Basically, when you got bromine bonding with bromine, they each have a spare electron that they can share together. Which tends to be how they are. But then if they separate out, then they'll separate and they'll have their own electron, and it won't be bonded within the middle. And now they're called radicals. I don't know why they're called radicals. I guess because they react so heavily. So they're like radical, like that kind of radical. But I don't really know. But yeah, you can get your two bromines, but they don't like to stay apart too much. They like to bond back together. But within a free radical substitution, we actually can start to use the fact that they react with everything. So what happens is we first have, I think it's UV light, form of electromagnetic radiation. It's not particularly important for the mathematics we're going into, but I guess I'll throw it on there just because. And then we got two bromines. And what will happen is going from here, we'll put in N as 1, so we've got CH, Cn, so that makes C1, 2N is 2 plus 2, 4, so we've got CH4. What tends to happen is you got your bromine, let's say the atmosphere or whatever, you got your CH4 here, and there's like billions of each, so there's loads of CH4 around. Loads of Br2. And you got a UV light suddenly concentrates on a particle because maybe that just happens. Splits into two bromine radicals, but instead of sticking back together again, because it's so reactive, because it wants to move to being as less reactive as possible, it will like tend to react with your CH4. And it like tears off a hydrogen, I guess. What does it leave? Oh yeah, and the bromine bonds with the hydrogen. So it's like we had four hydrogens, but now one of the hydrogens is left, so it's leaving just that part of the bond there. And the H string goes off and it bonds with the bromine. Like a bromine would bond it with itself, but here it's bonding with the hydrogen instead. I wonder how much sense this makes. Maybe it makes none. I don't really know. But now we've got a CH3 radical, and radicals like to just react with everything. And we're saying we've got excess of CH4 and Br2 in the atmosphere, so if we've got a CH3 radical and it wants to react with whatever it can, tend to react with the Br2. BrCH3. And what's left over? Oh, the other half of the bromine. But the thing is, from this process, we've ended up with another bromine radical. So we started with a bromine particle, we split into two, but only one of them got used. What it means is because we get another one, it means we can throw this back in the start, and we can just keep looping this forever, basically. So what does this mean? That's a great question. What it means is yo, how's the UV light split the Br2? Oof, great question. I actually know this one. The fact I know this is actually surprising. The interesting thing really is, why is that not the same for hydrogen? I can explain why, roughly. So everything pretty much, unless it's really big, follows quantum mechanics, and quantum mechanics says that all energy comes in packets. So when you have energy, for example, light energy, UV light, it doesn't just come as light, you have packets of it. I'll draw these packets like this. And only one light packet will interact with the bond at once, and it just so happens if a light packet of UV light hits this bond, because the UV light packet is bigger than the bond energy, it breaks it. But in hydrogen's case, because the bond energy is bigger than the energy packet, it absorbs it and then it doesn't break. So hydrogen and UV light doesn't split up, but bromine does. But the fact I know is actually quite surprising. I don't remember why I know that. I think I was just reading around this at one point. But I'm kind of more interested in because basically TJ, can I call you TJ for stream? Can I call you TJ? I guess that works. Basically, so we have this equation, right, which we got from wherever, and it states that it can terminate. So you got Br2, 2 lots of bromine radicals. Bromine radical goes in, creates a methyl radical plus hydrogen bromide, and then you have this, and then this loops forever and it terminates. I was wondering, how does that actually work in terms of like physical space? So I have like 3 theories of how it could work. The 3 theories, I'm calling them like 3 ways of how this reaction could occur in 3D space. So I'm calling them catalytic, simple molecular. I'm just going to put simple because oh wow, that's an interesting semicolon. What's the other one? Oh, branched. And basically I wanted to model all 3 in Python 3, so that's what I'm going to be doing. I can't decide which one to choose first, but I guess I'll try and like explain it. So Br, the catalytic one, you have your Br2, then it splits into 2 lots of Br. And then you have your regular shenanigans with Br going to CH4, and then that turning into a methyl radical, and then another bromine coming in. So we have a second Br2 going in. Oh, I should have drawn this diagram before. You live to learn. And basically what all of this does, does this make any sense? Because you start with your Br2, and that turns into 2 bromine radicals, but then you put a second Br2 in, because wow, this is getting messy already. Because you have your first Br2, but then you have a second Br2. So we got two bromine molecules going in. And what we have coming out is we have CH3Br and what's the other one? Oh yeah, HBr. We have those 2 things coming out, but in addition to this we have 2 bromine radicals. Because we have 1 bromine radical from the start, because we only use 1 of them. We have a second bromine radical from the end of the reaction when we put in a second Br2. So basically, my theory as to what happens with this is I was like, well, to me at least, it makes sense if these 2 bromine radicals just bond together to make a separate bromine. But then if that's the case, what that means in terms of our reaction is that we put in Br2, put in CH4, and then we get out. Oh, you still there? Or no? Okay. I don't know. I'll explain whoever's watching anyway. If there's only one here. No, that's chill. We get out these 2 products, but we also, in order to get out these 2 products, we actually had to put a second bromine in. So we had our first bromine for the start. We had our first bromine at the start to get our first bromine radical. But then we also inputted a second bromine here, like I said. So we actually needed 2 bromine molecules. Yeah, is this making any sense? So because we had to put in 2 bromines, but then we got an extra bromine out, it means that we had to put a bromine in to make it work, but then we get a bromine out. So it's like with our free radical substitution, it's like we're looping a bromine 2 over the top of the reaction occurring. So it's like Br2 is like a catalyst, so it keeps like cycling around while the reaction occurs. So we keep putting in Br2 and keep putting in CH4, and then we loop around a Br2 and out comes CH3Br and HBr. But then the Br2 never gets used up, it keeps like swapping in and out. This is like ridiculously complicated to explain, but I'm thinking Python it might make it clearer, maybe, I don't know. So that's one thing I could do in Python, but then there's the other 2 I can do. Simple is the simplest and actually makes sense. It's really, really simple. but I don't think it's particularly common because of the way it works. It breaks two of the rules that I set up just before stream. I haven't spoke about the rules on stream. I might talk about the rules. They'd be useful, but also it'd add complexity. Maybe I don't want to add right now. I don't know. The other method is, oh well, put in our bromine. And what happens? Oh yeah, we use one bromine for the reaction of bromine with CH4. But then this model of free radical substitution suggests like immediate termination. So we got CH3, it's HBr. But then even before the next step is complete, where CH3 reacts with Br2, a second Br2, this model suggests that like we immediately terminate. So immediately CH3 reacts with that other Br2 from up here. So we don't even do one cycle of propagation before it's over. So this example is probably easiest to code, but I don't think it's particularly realistic because I think that CH3 tends to react with Br2 more than Br radical. But that's just a guess, I'm not really sure. Because if it didn't, then why would we have this as our general equation rather than this? Because this is way simpler and makes a lot more sense. So that's simple. Then catalytic, which is the bromine cycling on itself theory. And then branched is probably most likely to be realistic, but it's also most annoying and complicated to draw out. But it like follows the rules and it sort of makes sense. So this model, oh, it might be nice if I had done it. Might be nice if I had done it like this. Boop. So this model suggests, let's do pink. You got your Br2. UV light enters the bond, breaks it up into pieces. We got Br radical on one side, Br radical on one side. And basically, this model suggests that the two happen side by side. So on this side, you have your reaction occur. Oh, it's getting too far across. Ah! That's gonna cause problems because we're not 100% node. Eh? I'm doing bad things. Oh, it is 100%. Okay then. Oh, it's barely gonna fit. Let's do it. Yes. Oh, that's our CH4 input. Oh, but I need the input to. So we've inputted two things. We've inputted the Br2, which is going to split into two branches. Then we're inputting our CH4 for this iteration. Then we need to input our Br2. So every iteration for this, you input CH3, CH4, Br2, standard stuff. So in this reaction, we got CH4 plus Br2 gives our two products HBr and CH3Br, but it needs an extra Br2 at the beginning. But then the two happen on side by side, so I'll draw the other side in a second. If anything's making sense. And then we get to recycle, well not recycle, but we get a new Br radical to replace the previous one. Then the idea is we can copy this. Oh no. Hopefully can. There we go. And then we can say the same's occurring on the opposite side. So you can say for the bromine split we have the bromine on this side doing the reaction, but the same reaction occurs in parallel. That makes sense. is what this theory is sort of suggesting. And we can just keep repeating it as long as we want because we keep making bromine radicals. So that's pretty neat. And then for termination, at some point what would happen is we'll have a make our primary methyl radical, CH3 radical, and then HBr. Oh, we're going miles across again. No. Rip. That is sad indeed. Oh no. Go. Yes. Is it gonna paste? Oh boy. Answer. Oh no way. What? Nice. Yeah, it's just paste at the top. Can we scroll while moving it? Oh, we can. Oh, that's pretty glitched. So you got that occurring here. We've also got that occurring on the other. Ah, I forgot. Oh no. That worked. Okay. Yeah, go. We've also got this occurring on the other side. But then what we say is that, okay, and that's just that. Nice. What we say is another bromine just comes into the mix. Splits into two bromine radicals. And then instead of it continuing by bringing in another Br2, this cycle it doesn't bring another Br2, we only bring in CH4 on either side of the system. And then we terminate it with an extra Br2, so now we've got two bromine radicals. These two can come together to terminate, to cause CH3Br. Yeah, what do you think of this theory? Does it hold up or not really? I have no idea. It's completely theoretical. I have no idea if this is actually how it works. But I've got three models that I think make up for all the ways it could work, unless there's another way I've missed. Maybe. Oh wow, that actually didn't take as long to explain as I thought. We'll write it out anyway, I don't know how well I explained. And then, so these sections here can terminate as much times as it wants, as many times as it wants, because it keeps producing a new Br. So we have to have a Br2 to start it, and a Br2 to end it, but other than that, the ratios of because the overall reaction is bromine reacts with CH4. Make CH3Br and HBr in a 1:1:1 ratio, and it can keep looping. But in reality, if this is the system it uses, because we had an extra Br2 at the start, and then we do a less one. Oh, we only do one here instead of two. Oh, so this equation does. But when you see this equation, you just think about the middle steps, but really you have to think about a Br2 on the top and one less at the bottom. So because we have one more at the top and one less at the bottom, because what we'd have instead of having one at the bottom, usually if it didn't end, if it repeated, is we'd have Br2 on this side. We'd also have Br2 on this side, so it can continue. But here we haven't got one on either side, we've got one for both of them, hence causing it to terminate, because we split into two bromine radicals. I don't know if this is a foolproof model, but this is what I'm thinking in my head. So I explain the three ways that I think it could occur. Guess I got to choose one and do it in Python. I have no idea how this works in Python. It's going to be a learning experience. So simple seems like the simplest. I really like catalytic. I don't know if this is realistic in the real world, but I love it. Especially this diagram here to explain it. Branch seems realistic, but it also seems kind of lame because it's so realistic. But it's probably important because it's more realistic. This is my simple one. Let's try and do this in Python. Oh gosh, how does this even work? And now we have fun times. I think we're going to immediately have to go into an object-oriented paradigm thing. So let's say molecule so we're going to need ID. How's the IDs going to work? I guess we can have like a Alright, so we're going to have a bromine flag up there. ID. Yeah. Oh, wait. Self.id equals ID. Oh my gosh. Is that the only functionality of molecule? And then class bromine is going to inherit from molecule. Is this how you want to code this? I'm not even sure. Oh my gosh. So now we're saying bromine inherits from molecule, it has an ID. Oh my gosh. Now what's the functionality of bromine? Define split. Wait, we need bromine radical first. This is such a theoretical idea. I had no idea going into this whether chemical mechanics and programming would mix. It's time to find out. Oh, we need to tell it inherits from. Oh my gosh. Let's go. Wait, but it needs to be able to. Bromine needs to be able to. Can I define a class within a class? Bromine radicals can only come from bromine anyway, so we can actually just straight up define this in here. Oh my gosh. That is the grossest thing I've ever seen. Let's go. Dot split. Return species. Oh my gosh. I'll try and explain myself when things die down in terms of complexity and novelty. But that's how you spell species. It doesn't really matter as long as I spell it consistently, but I'm going to spell it like that. As long as I consistently spell it wrong or correctly, it's fine. So what we're trying to do is we're trying to set up a class hierarchy for we can have this all lowercase, or we can have it uppercase. Doesn't matter, it's a flag. Doesn't matter, it's a flag. So at the moment we've got a molecule which we're defining as an object that can be initiated with an ID and assign the ID to itself. So we can just tell it what molecule it is. Then we're differentiating bromine as being a molecule that inherits from a molecule and that it can name itself. But it's going to be different in that it's got bromine radical self-contained within it. Which is like what is happening. Oh my gosh. that there's no flags. I need flags. Fortunately, the code doesn't get too bad, I think, hopefully. Append bromine radical. No, this is in the wrong place. So now it can know how to name the bromine radical. Or, this is getting pretty heavy duty. So now we've got bromine radical contained within bromine, which makes sense because radicals are of bromine. Because you can split a bromine into its radicals. I just don't know if Python will like it or whether Python will just throw up at how gross this is. We'll find out, I guess. Oh, it should have a method to name itself. Fine. What should I call this? Hello. No, that's terrible. As much as I want to call it that, I shouldn't. Get ID. At least it's well named. So making a bromine radical of its name, of its own flag. Oh, we need to put it somewhere so it can molecule.py, put it on the desktop. This is where this is too. From molecule import bromine, my bromine equals bromine. So what we're doing is we're saying we now own a bromine, set up as a bromine. And now we're going to say my radicals equal my bromine dot split. So we're telling it to turn itself from a Br2 into 2 bromine radicals in code. Oh my gosh. This idea might have actually been sick. Or maybe it's gross. For radical in my radicals, print radical dot get ID. This somehow works. It's going to crash so hard. Oh no, what part didn't it like? Missing one required positional argument. I know what it is. We didn't tell it that it needs. That's fine, that was just us being dumb. Bromine radical is not defined. But it is defined. We defined it here. So it doesn't let me class within a class. Sometimes. Does it let me class if I class outside the class? No, that's not going to run. There's no code. Just definitions. Here's code. What? Why did that work? Oh my gosh. Look, we split a bromine into bromines. Oh gosh. Maybe that's better that it does it the way it does. We could put this in the super. So now get ID is common to all molecules. Oh, we called it molecule, it should be species, that's okay. That means I have to learn how to spell species. I automatically spelt it without an I just there. So why did I spell it like before? I spelt it without an I before as well. That means I'm spelling it consistently. That's good. Because I just realized it's not a bromine radical isn't a molecule. It's a species. So that way we can keep it scientifically accurate. What? Let's go. Species. It can name itself. It can say what it's called. These two inherit from it, so they can name themselves and tell the world what they're called. This is now no longer necessary. That means we can tell the bromine to tell the world what it's called. Bromine has added functionality because it just happens to be a molecule, which means it can split itself into two radicals. Let's add a molecule so I remember. So now, if we wanted to, we could print my bromine.getID. So now we can see we got a bromine and then it splits into two. Oh my goodness, let's go. So now we can actually see what's happening control flow wise. Bromine splitting bromine, bromine radical, bromine radical. All right. Poor bromine. Bromine radical. So now we've got definitions for bromine, bromine radical. Now we can have, I want a new thing that's called species that exist equals an array. And we're going to put all the species that exist. They should automatically go there. Oh my goodness, we can actually do this. Okay, I'll explain. This is a class variable. Class variables are this is sick. Class variables are variables that are related to all things, instances of the class. So anytime we make a species, it'll be added to this, which is kept for all species. Oh my goodness. So now within the constructor we can species that exist dot append self. Oh my goodness, let's do it. Define get species that exist. Does that work? I have no idea. You can create a single instance, get species that exist. If that works, it'll be a miracle. Species that exist is not defined. But it is defined. It's because I haven't referenced what exactly it is. Does that work? That's because we never imported it. Missing one argument ID. I'm going to give it a flag of super for superclass. Oh my goodness. How can we make it not? Oh. It's getting extremely messy, but it's okay. Okay. Does that work? It's still adding the super class. Oh, I know why. We never put in super. Oh, that's trippy. Takes 2 positional arguments, but 3 were given. No, we only gave it 2. We never saved that module. Missing 1 required mission. Oh my gosh. We put in super twice. Everything needs super twice now. Well, that's annoying. Maybe flags should just be over there. This code's getting such a mess. Oh, let's go. Right, those are going there now. Because they seem to just want to be there, regardless of what I do. Self.id not equal to super, species.exist. Get ID self, return self.id. Bromine species. Self ID. So now we can just shove its thing right in. Can I? Let's hope that these, I hope that these are within the active memory space, but I don't know. Big problems. What is happening here? What have I done? Bromine radical flags. If those do work, I don't know if it works yet though. Deleting a lot of code. Just gonna have to hope it works. If it doesn't, I need to come with a better solution anyway. Wow, this would save a lot of code if it did work. I'm assuming even though the species requires an input, the inherited ones don't, the differentiated ones don't, hopefully. We don't need an input anymore. Oh no, please work. Bromine is not defined. Why is bromine not defined? Oh, because we're trying to do it wrong. Ooh. I wish you could define classes within classes, but I don't think you can. Probably a good reason why you can't. Maybe you can, but I wasn't doing it properly. Okay, I think the way I want to do it for now is triple S indicates that you don't want it to be a regular thing, you want it to be a special one. So if it's not SSS, do that. Else equals super. That might be it. I'm trying to comprehend what's just happened. So we've set up bromine, and we've said for bromines that exist, print species.getID. Yeah, we can have another one that says output species that exist. That might be good. Now we can turn this into it doesn't like it because it's a colon. That still works. Oh, it'd be nice if it appended it, all of them. We can do that, no problem. So if I do this again at the end, the bromine's in there. So what we're wanting is this array to hold everything that exists, and we want when the bromine splits, obviously we want it to remove itself. Alright, we can have one that's called doesn't exist. It's going to look like that. So much work just to have this working, but it'll be cool once it works. Let's have a script at the moment. So now this should just print. Oh, I should say bromine created as well, shouldn't it? This might be cool. So now I'll say bromine created, bromine. Can we do this in the shell? that does actually work. My bro 2 equals bromine. I'm going to define this as being R. It's a lot of work, oh my gosh. But now this is assigned to this, which is assigned to the array of stuff. Be nice if you could say which one, but I think that's too advanced for now. Yeah, it's all for chemistry. It barely does anything. I can show you the code. So what I wanted to do, right, is I wanted to have like an interactive thing where you can do stuff. I'll show you. So it'd be like if you wanted to, so at the moment, so what you can do is this command is the most important one really. It's too long for how important it is. I'll just call it display. So the display command shows you what molecules. Why does it do it twice? Ah, because it does that by default. Why? Oh well, that's fine. But say we wanted to create a bromine. We can do that by doing a bromine equals bromine. And now we've got a bromine, but then the idea is we could do a bromine dot split, and it would like split the bromine. And now we got, but then it should delete the bromine and turn it into 2 bromine radicals. So there'll be like a literal interactive like chemistry display thing for molecules and radicals and stuff is the goal. I'm not succeeding too well at the moment. Oh, I can fix it really easy. But yeah, this might be cool when it exists. It might not. Why does it print it twice though? Oh, because 2 bromine radicals created. That's actually sick. But then we don't really want it putting it out twice because we need it to split simultaneously. Interesting. Could probably do that. Yo, this is actually cool. Then we can have rad equals. Can code it straight in there too instead of using the console. It's still got it as two bromines. They still happen at different points in space. Ah. All right, we need a new method within the super called destroy. Doesn't exist. And then with our output, we need both for our output and get. I guess I should put it in both. Yeah, I probably should. Array. I can't be bothered. That'll work. If element not equal to doesn't exist. So in other words, if the element exists, array.append element. Then right at the very end, we're going to do the big game changer of equals array. And this way we can do underscore strip all entities. So basically what we're doing is getting rid of ones that have been deleted, so things can be destroyed. Now when it splits, self dot destroy. Yeah. Or do I want that afterwards? Put it afterwards. Boop. How did that work? Bromine created. Bromine radical created. Bromine radical created. Oh, now it doesn't have. That should have been removed. But it remained there. Why? But why? Now that is a big question mark. Oh boy. Interesting. This is going to infinite loop, isn't it? Let's do it anyway. Oh, I love that infinite loop. Oh, it won't even end. Oh, this loop is too powerful. How do I debug then? But why doesn't it work? Object-oriented programming is just the worst sometimes, always. It's not getting rid that doesn't exist. But why? Alright, here let's do 4 elements in array. Dot. Oh no, nothing's working. You win some, you lose some. It was fun at first, and now I was like, nothing's working. So it's in the array, but why is it? How did it get into the array? Clearly didn't want to be reassigned. Can we do that? I don't know if it's going to change anything. Let's try that. I don't know if it's going to work. It's coming. What's it done? Not a whole lot. I'm stuck on it destroying itself. Very stuck on it, that. It's funny because it's like such a great analogy for chemistry too. In chemistry you can't have things be created or destroyed. So it's like if you have like hydrogen reacting with like oxygen or whatever, none of the atoms are created, so where this creates, what does it create? It's just H2O. Well, it can't be just H2O, it has to create something else. Then what else? Can't make CO2, there's no carbon. In combustion you usually get that. completely forgot how this works. Oh yeah. Oh yeah. So yeah, so you have to do like number things because you can't destroy or create things because destroying things just doesn't happen. And it seems like in my programming destroying things isn't happening either. Unlike with atoms, you should be able to destroy things, but it's harder than you'd think. The programming languages don't ever make it so easy to delete stuff. It's a big problem. Single array is fine. But why? Because when we create a new bromine radical here, it'll run the init and the super. When it runs the init and the super, it should, so appending itself, output species that exist, and then it should get rid of the doesn't exist entities. Oh, I found the problem. That's so annoying. Because element isn't a string. It's an object, and we need to tell it to become a string of its ID. Oh my gosh, all that for one small error. It'll work now. Like 99% certain. I've got to clean up my mess. Oh, such is life. Well, at least I found the problem. Now we just got to clean up. Let's get rid of all this. That's just debug. It's a weird way of structuring the code, but it doesn't matter. Because I was doing weird things because debug, but that's fine. I think I've gotten rid of everything that's doing bad things. Bromine created, bromine radical created, bromine radical created. Let's have a print statement in the split. Bromine created, splitting a bromine, bromine radical created, bromine radical created. Oh my goodness. We're getting somewhere. I can't remember which one I'm doing. I'm doing this one. And then we can do products 1 equals, oh, we need to have a reaction method. Oh my goodness. Reaction method. Dear. Oh. So far we've got bromines that you can make, bromines that you can split. Oh, I should add some others. Oh, it's all going to have to go on the same code. Oh well, it'll be fine. Can methane only react to the bromine? I guess in our model it can only react with the bromine radical. Alright, we need methane flag. Brom rad react. Self. Oh no, is that how we want to do it? I don't know, there's so much going on. Oh, I don't know how I feel about this. Turn some of the chemicals into classes in Python. Might be kind of funny just kind of for the meme at this point. This was cool. This idea worked. Talk you through that theory of the three ways. But programming it into Python maybe wasn't the best idea. It's pretty funny though. I might finish the simple one just for the meme. Well, maybe it's cool. But I need to think about how it's going to work. Oh, I guess. Ooh, program architecture. What I'm thinking is for bromine, let's write an M for method. So for bromine, the method goes here. So on the bromine, we call the method split. But then for other things, like for example with BR, CH4. Can we do the method on CH4? Does that work? No, it doesn't, because it becomes a new thing. Right, no, it can work because we did it with the bromine. So it would return a CH3, even though it doesn't own a CH3. It brings it into existence, and it can bring a HBr into existence. And it can tell the bromine to kill itself, and then it can destroy itself too. Yeah. So for those ones, the method can be on itself. Would it be clearer through one reaction, one no, it wouldn't. But then for ones where it's a thing with itself, so example, joining two bromines, it's going to have to happen for a super, because otherwise it's confusing. It's not clear which one it should go on. Could do either, but that'd be kind of messy. Be easier to do it on the super. Alright, so that's the architecture. Oh, I forgot how to do that. Alright, well that was fairly productive. I'm not sure how well explained it was though. It's a pretty interesting, fun project. We've literally spelled out some some molecules from chemistry in Python 3. So that's pretty hardcore. Yeah, that's it for me. I need to go to sleep now. Hope you found something interesting here, maybe. I don't know. See you around. Bye.